Well, thank you very much for the introduction. Today I'll be talking to you about our work of laser cooling and trapping ultracold molecules. And as a brief outline to my talk, I'd first like to begin by talking about why are we interested in ultracold molecules and their applications. And then from there, I'll move on to working to actually control these molecules, specifically focusing on diatomic molecules, and specifically the work we've done on calcium fluoride. And then I'll end by looking at pushing this laser cooling technique that we've now developed for these diatomics onto more complex polyatomic molecules. So let's begin by talking about why we're interested in ultracold molecules. Well, there's many different reasons for this. One reason is that ultracold molecules are very good for precision measurements. This fundamentally has to do with the fact that ultracold molecules have near-degeneracies in their energy structure. And these near-degeneracies lead to an enhanced sensitivity to external perturbations, which is what you're looking for in a precision measurement. And because of this, many molecule experiments actually set some of the most stringent limits to precision measurements. One of the most famous examples of this is the electron EDM searches, which currently molecules set limits to this, which actually far exceed the mass ranges that can be accessed by the LHC. One can also study cold and ultracold collisions in chemistry. And there's been a lot of work in this field across many years, with the pioneering work back at JILA several decades ago now, of really quantum state control of these molecular collisions. And more recently, there's been a lot of work focusing on really the complex dynamics of what happens when two molecules collide. This often goes in the name of sticky collisions. And now there's also more recent experiments that can actually map out the product state distributions of these very complicated reactions. And finally, and probably the reason all of you are here today, is that molecules can be used for quantum simulation and quantum computation. And why is this the case? Well, ultracold molecules have several nice advantages for these applications. Namely, they have strong and tunable anisotropic long-range interactions. They have a rich internal level structure, which means they can be coupled to a wide range of different optical, RF, and microwave fields. The system, all of these long-range interactions actually happen in their ground state, which means that this gives rise to the fact that molecules tend to have very, very long coherence times when you compare it to other types of systems. And finally, the system as a whole is easily scalable, as I'll talk about today. And because of these nice advantages, there's been a lot of theoretical work over the years of looking at various quantum simulation models that can be done with ultracold molecules. And also more recently, a lot of work looking at quantum computation using these ultracold molecules as qubits. And specifically here, I'd like to highlight some work from the QSUM collaboration, which looked at two calcium fluoride molecules in optical tweezers, which is the platform I'll be talking to you about today. And they see with very reasonable experimental parameters that one can achieve in the near future, one can expect 2-qubit gate fidelities of well over 4 nines. So this seems like a very promising platform. And there's also been theoretical work showing that using ultracold molecules as qubits actually naturally leads to a way to do quantum error corrections for this system. And one of the most promising platforms that really has taken off over the past few years to use in specific ultracold atoms for quantum information and quantum simulation are these rearrangeable optical tweezer arrays, where one loads individual atoms into these tweezers, and then one can rearrange them into any arbitrary dimension in 1D, 2D, or even 3D now. And this, of course, has a very natural extensions to ultracold molecules. One simply has to replace these ultracold atoms in these tweezers with ultracold molecules. And that's what I'll be talking to you about today, our work of loading these ultracold calcium fluoride molecules into optical tweezer arrays. Now, how do we actually go about producing ultracold molecules? Well, over the years, there's been really two different routes that this has taken. The first is an indirect route, whereby one starts with ultracold atoms and then associates them into ultracold molecules. The route I'll be talking to you about today is a more direct method, where we actually start with molecules at high temperature and then directly cool them. And specifically today, I'll be talking to you about laser cooling these molecules down to microkelvin temperatures. And this laser cooling technique, of course, has many nice advantages. First of all, we get access to all of the laser cooling techniques that have been developed for atoms over the many past decades. And of course, we can then image and non-destructively detect our molecules. And also, you'll see that this laser cooling technique actually turns out to not just be limited to molecules where each individual species is laser coolable. And this means that actually it turns out that you can laser cool quite a wide range of complex polyatomic molecules, which I'll talk about a bit later on today. Now, nevertheless, laser cooling of molecules is challenging, as was alluded to earlier, which really has to do with the fact that when you excite a molecule up to some excited state, most of the time it will not return back to the state it started. It will return to some other rotational or vibrational state of this molecule. And really the challenge of laser cooling these molecules is to engineer a way such that you have a molecule that always returns, or at least preferentially returns, to the state you started in. And it turns out that there's a way to do this. So let's first look at the rotational states of these molecules. And it turns out that actually rotational closure can be achieved by simply photon cycling from an n equal 1, and here's the rotational quantum number, n equal 1 to n equals 0 state. And because of parity selection rules, this will always decay back to the n equal 1 state. And this means now you're rotationally closed in your photon cycling. As far as vibrational states are concerned, unfortunately, there are no nice selection rules like this. But it turns out there's actually a very large class of molecules that support laser cooling. And this type of, these molecules that support laser cooling are shown here. It's basically you have a metal-centered s orbital, and it's connected to some sort of ligand. And because of orbital hybridization during the bonding process, what actually happens is that the electron wave function around the metal atom actually gets pushed away from the molecular bond. And why is this nice? Well, this means now that you've basically decoupled your electronic structure from that of the molecular excitations. So in essence, you have a molecule, but it's almost atom-like when it comes to laser cooling. And when you have this sort of structure, you'll see that the vibrational branching ratios are highly suppressed. And this means that with a limited number of repumping lasers, we're able to cycle many, many photons and actually achieve laser cooling on these molecules. And because of this, there's been a wide range of different groups working on this, with pioneering work back on strontium fluoride back at Yale and Dave DeMille's group, and more recently work on other molecules such as yttrium oxide, very light molecules with UV transitions, and then molecules that can be used for both EDM sensitivity as well as other precision measurement and chemistry relevancy. But today I really like to focus just on calcium fluoride. So how do we actually go about laser cooling and producing these molecules? Well, the pathway is shown here. So we begin with a molecular source where we create these molecules at high temperature in an ablation source. And then we use buffer gas cooling to cool down both the external degrees of freedom as well as the internal degrees of freedom of these molecules down to cryogenic temperatures. At this point, we can then basically switch over to normal laser cooling techniques of laser slowing as well as magneto-optical trapping to greatly enhance the phase space density of our molecular sample. And then finally, we can do further subdoppler cooling and optical trapping of these molecules. Now, of course, because this is a molecule, there's of course more complications that arise at each of these steps. So let me first focus specifically on this magneto-optical trap. So many of you are probably familiar with how a magneto-optical trap works. In an atom, you typically have what's known as a type 1 MOT, where you have more excited states than ground states. And this means that you can apply your sigma plus light and sigma minus light to create a restoring force, and you always end up decaying back into a state that's not dark. But I mentioned earlier, in order to achieve the rotational closure that we needed to cycle on an n equal 1 to n equals 0 states. So what does this mean? Well, it means that naturally we now have more ground states than we do excited states. And this means now that when you go to make your MOT, for example, and you start applying your sigma plus light or sigma minus light, you'll very quickly pump into these dark states over here. So this is kind of a reoccurring theme at every step along the way, that when you try to do photon cycling in molecules, you'll always end up with some sort of dark state, and you need some way of remixing them. And specifically, the way we remix this is by making what's called an RF MOT, where we simply switch both the polarization of the light back and forth at the scattering rate, as well as the magnetic field of the actual magneto-optical trap. So in this case here, we switch both of these at about a megahertz or so. And with this, we're able to create a magneto-optical trap that looks not so dissimilar from your atom MOT. But you'll see that the temperatures and densities are significantly lower than you might find in your atomic species. So in these early MOTs, we used to get about 10 to the 5 molecules, and now we've upgraded this to get well over a few million molecules on a regular day. Now, you might ask, why is this temperature so hot? Well, this has to do with the fact that you actually have subdoppler heating forces within your molecule, Sisyphus-like heating forces within your molecule. Now, we can actually make use of these Sisyphus-like effects by, instead of having our MOT beams red detuned, as we typically have when we make an actual MOT, we can then blue detune these MOT beams, and now go about doing what's commonly referred to as gray molasses cooling. And the idea here is that in the molecule, we have both some dark state and a bright state, and you rely on motional coupling from the dark state into this bright state. The molecule rides up this potential hill that's just set by the AC Stark shift of your light, and then gets excited up and falls back down. And the Sisyphus-like cooling effect gets repeated over many times, and this cools your molecule further. There's one more trick we can pull from the atomic community, which is including something commonly referred to as VSCPT, or velocity selective coherent population trapping. And here the idea is that if you have a 3-level system as shown here, you'll have a coherent dark state at 0 velocity. So now if you combine both of these features together, your gray molasses cooling will give you cooling for molecules at high temperature, and then you'll have an additional dark state right at 0 velocity. And we can see that as we tune over these, basically this 2-photon detuning, we see that we reach a minimum temperature right when we're on resonance with this lambda structure. And here now we reach temperatures down to about 4 microkelvin or so. So this is about 10 times the recoil limit of the photon. Now that we have nice cold molecules, we can then optically trap these molecules. So this is done as you would typically do with atoms, where we simply shine in a far detuned light trap. And then we also apply laser cooling light, specifically this lambda enhanced cooling light, to cool the molecules from the molasses into the actual optical dipole trap. And the fact that you see that this number goes up as a function of time means that the cooling actually works in the presence of the optical dipole trap, which is actually not a given for molecules because you have many different tensor Stark shifts which can easily mess up this cooling. And we see that now at basically every step that we do in the experiment, we greatly increase the phase space density of our molecules. Because we can actively cool the molecules in the presence of this dipole trapping light, it means we can also actively image these molecules by simply capturing the fluorescence from these cooled molecules. So in a sense, we now have kind of everything we need for single-shot detection of single molecules. So now that we've achieved this, the next thing we moved on to is to actually load these molecules into optical tweezer arrays. So this is done by simply overlapping these very small tweezer traps with the optical dipole trap and loading the molecules from the optical dipole trap into these small tweezer traps. And we once again see that the phase space density increases further, and we're able to now take sequential images of our optical tweezers with fairly reasonable fidelities and survival fidelities really just set by the collection optics that we have in the experiment. So now that we've gained this single particle control of this molecule, we can now move on to actual single quantum state control of these molecules. And we can do this within these tweezers by a combination of optical pumping pulses and microwave pulses. And we can drive nice Rabi oscillations within of these molecules within each tweezer. So now that we've gained this quantum control, the first thing we actually did was to go back and now study collisions between molecules. So this tweezer platform actually has a very nice method of doing this. We can simply load 2 tweezers, each with a single molecule, and then we can merge the 2 tweezers together. We wait for a variable amount of time for the collision to take place, and then we can re-separate them and then re-image the final products of these collisions. And what we see is that when we now do this experiment, but we post-select on experimental cycles where only one of these 2 tweezers are loaded, we see essentially no loss, because there's no other collisional partner for the molecule to collide and react inelastically with. By contrast, if we now post-select on experimental cycles where both tweezers are loaded, you very clearly see collisions taking place and decay in the survival as a function of time. So from this, you can then map out the actual rate coefficient of these various collisions. And we can also do this for basically any internal state of the molecule that we want. And what we see is that basically no matter what state we saw it in, the collisions would always end up at basically the universal loss rate. So this is again a reoccurring theme in ultracold molecules and ultracold collisions, which is when two molecules collide, they tend to collide inelastically, basically always at the universal rate. And there's many different reasons why this can happen. One of the leading theories is the fact that when these two molecules come in and collide, they form some sort of collisional complex, and then the far detuned tweezer trap light will very quickly photoexcite this collisional complex, and that will cause your loss. Now, we're not so interested in this loss. We'd like to really suppress this loss, right? Because we would like a nice, stable, dense molecular sample. So this brings about the idea of shielding molecular collisions, where really what we want is we want to prevent the molecules from ever reaching this short range where they can undergo inelastic loss. And there's many different ways that we can somehow basically prevent these molecules from reaching short range by using different types of external fields and controls. So there's ideas on how to use electric field shielding, microwave shielding, optical shielding. All of these different methods basically always do the same thing. They just they tune the interactions between the molecules so you have some sort of repulsive interaction between them. Specifically, we focus on implementing this microwave shielding scheme on these molecules. And one of the very nice things about this microwave shielding scheme is that not only does the inelastic rate get suppressed by this shielding, the elastic rate actually increases by almost an order of magnitude. So if you want to do, for example, further evaporative cooling of these molecules, this is of course very useful because you want the highest possible ratio of elastic to inelastic loss. Now there is a slight complication to this, which is in order to actually create this shielded dress state, this actually requires us to apply very high power, cleanly polarized circular microwaves within our chamber. And of course, there's several other complications here, namely that you're at 20 gigahertz, so you have absorption within all your different materials. You have to worry about phase stability. But we're able to create these circularly polarized microwaves with these helical antenna arrays. But one of the main limitations that was not known before we did this was that it turns out that all of this shielding tends to be limited by actually phase noise of your microwave source, and specifically phase noise at the Rabi frequency that you're at. So the idea here is that in the dress state picture, you have some sort of shielding repulsive potential as well as an anti-shielded potential. And ideally, all your molecules are in this shielded dress state up here. But now if you have phase noise on your microwaves at the Rabi frequency, this is simply a direct drive from this shielded state into this anti-shielded state, and this will cause loss. But once we've figured out all of these complications, we're then able to create these very cleanly polarized circular microwaves and drive the molecules at about 30 megahertz or so of Rabi frequency with a ratio of about 100 to 1 in cleanliness of the circular polarization. And this then allows us to then actually shield these molecular collisions. So again, we repeat the exact same process we did earlier where we load two individual tweezers. But this time, after we merge the two together, we then turn on this shielding to prevent the inelastic loss from taking place. We then reseparate and then image them. And what you see now is that the gray curve here shows the loss versus time of the unshielded molecules. But now when we prepare them in this shielded dress state, you see that the loss rate is very much suppressed. We can also create them in the opposite dress state, which is this anti-shielded state, and you see that the actual loss rate will actually increase. But really, basically the take-home message here is that we're able to shield the inelastic loss by about a factor of 6, but maybe more importantly, we're able to reach a ratio of elastic to inelastic loss of well over 50 based on this inelastic loss rate. So now that we had this inelastic loss rate mapped out, we wanted to just double check what is the actual elastic loss rate to make sure, verify that it is indeed a factor of 50 higher. And sure enough, we see that when we prepare the molecules in this microwave dress state, we see that indeed the elastic collision rate increases by almost an order of magnitude. And this verifies that we do have indeed this very high ratio of elastic to inelastic loss. We did try some quick evaporation of these molecules, but we simply didn't have enough density compared to our dress state lifetime to make this, to have this be very successful. I do want to point out some more recent work from MPQ, which has now used the same technique, but on fermionic NAK. And because there they have a much denser initial sample, they're able to very effectively evaporate their molecules down to below quantum degeneracy. So now that we have the collisions under control, the last thing really we want to look at is what is the actual coherence times we might have of these molecules within tweezer traps. And it turns out that with the combination of some magic angle tricks to basically reduce the amount of light shifts that we have, we see that we can get a Ramsey coherence time of about 100 milliseconds and a spin echo time of about half a second or so. But maybe even more promising is that if you actually look at what is limiting this coherence time, you'll see that the coherence time is simply directly linearly proportional to your temperature. And this has to do with the fact that as the molecules are hotter in your trap, they explore more of the trap volume and different intensities of light, which all have different tensor Stark shifts, and this causes the decoherence. So if then there's a way to further improve your cooling of these molecules, it's natural to expect to have much longer coherence times on the order of several seconds. But nevertheless, even with the 100 millisecond coherence time that we have here, this is still a coherence time that's much longer than the predicted gate times between, say, two CaF tweezers. So in a sense, this is already appears to be a useful qubit in the future. So now we've been working on several upgrades to this experiment such that we can actually reach for cooler temperatures. Specifically, we're working on Raman sideband cooling of these molecules within these tweezer traps. But now we're also scaling up for higher NA such that we can have much higher imaging fidelities and create larger arrays. So just a few highlights from the new apparatus. We're now able to create molecular MOTS an order of magnitude denser. And we're able to now do rapid optical transport into a glass cell where we can then load these high NA optical tweezers of calcium fluoride. So as a brief outlook on the calcium fluoride side, so as I mentioned, we're working on actually demonstrating Raman sideband cooling of these molecules within these tweezer traps. And then we also want to, of course, demonstrate dipolar interactions between two individual CaF molecules and two tweezers, and then move on to 2 qubit gate demonstrations. At that point, we can then think about moving on to doing quantum simulations of spin lattice models, as well as basically tailoring our qubit pulses to get some optimized qubit pulses to have even higher fidelities. Down the line, you could also imagine further increasing the coupling strength between your tweezers in various different ways, either by using a nice proposal by Mike Taubert's group, whereby you can use the tensor Stark shifts of the actual molecule to load basically 2 individual molecules within a single trap. Or you could also think about a hybrid system where you combine molecules with Rydbergs and try to get the best of both worlds. And with that, I'd like to thank the CaF experimental team, so Yi Cheng, Sean, Scarlett, Derek, our PI, John, as well as our co-PIs, Wolfgang, Conquin, Unmi, and Thijs for the theory on the shielding. Now, everything I've talked about so far has been with a diatomic molecule. But I mentioned early on that all of the laser cooling actually takes place around the metal atom of this molecule. And the ligand itself doesn't really actually participate in any of the laser cooling steps. So it's natural to think, well, what if we replace this simple ligand with something more complex? Or let's take this to the next step and add something even more complex to this molecule. Would this still be laser coolable? Well, it turns out the answer is yes, this is laser coolable. But maybe let me first step back and say, why would we even want to do such a thing? And this has to do with the fact that when you scale up in this complexity here, specifically going from a diatomic to a polyatomic or triatomic, the main thing that you gain is now you've gained angular momentum around your internuclear axis. And this angular momentum around your internuclear axis then gives rise to near-degenerate parity levels. And these are the near-degenerate parity levels that you use to actually couple your molecules to fully polarize them and have long-range interactions. So the presence of such doublets is actually a generic feature of these polyatomic molecules. And you see that because they're closely spaced, it's now much, much easier to fully polarize these triatomic molecules than it is to polarize their diatomic counterpart. Where the diatomic counterparts, you would tend to have to apply tens of kilovolts per centimeter. These can be fully polarized at a much, much lower field, which is, of course, very nice if you're trying to do precision measurement or trying to beat down any sort of systematic effect in your qubit system. The other thing I want to point out is that not only are the polyatomic molecules here fully polarized, you'll see that there's actually another state here that is actually a state with zero dipole moment in the lab frame. So this means that while your molecules are fully polarized, you can easily turn on and off your long-range interactions by switching between these two states. And because of these nice features, there's of course many different extensions to what I talked earlier about using ultracold molecules. On the precision measurement front, now you can combine basically the laser coolableness of these molecules with an EDM-sensitive molecule while still maintaining nice features such as co-magnetometer states, which are used to cancel out systematics. And there's been some preliminary work that has looked at these systems, and it looks very promising in the sense that with reasonable numbers, one can expect basically a few orders of magnitude improvement on the current EDM limits using these polyatomic molecules. One can also imagine looking for other precision measurement searches, specifically looking at ultralight dark matter, where here now you're using the fact that these polyatomic molecules have various internal degrees of freedom. Specifically, they have bending modes and stretching modes, and these would couple differently to if you had some sort of background dark matter. And by then looking at basically the transition frequencies of these two, you can map out if you have any sort of dark matter going through your experiment as a function of time. One can also, of course, continue studying ultracold collisions and chemistry, but now with molecules that are significantly more interesting to chemists. And one can also do quantum simulation, quantum computation now using these nicely closely spaced opposite parity states. But how do we actually go about achieving laser cooling of these molecules? So now we have a few additional degrees of freedom that we need to talk about from earlier. So if you look at a polyatomic molecule like CaOH, you'll see that now you have a CaO stretch mode. This is very akin to the vibrational modes you had earlier before in your diatomic molecule. But now you have also this bending mode, as well as some hybrid mode of a combination of stretching and bending. And if you actually look at what fraction of the population decays into these various different internal degrees of freedom, you find that they're still quite suppressed in the sense that in order to scatter about 10 to 100,000 photons, you only need to worry about on the order of 10 states or so, not thousands of states. So we've been able to do this. So we've been able to cycle well over 10,000 photons on this polyatomic molecule using about a dozen lasers or so to repump all of these different internal degrees of freedom. And with that, we can then repeat everything we've done earlier with our diatomic counterpart of CaF. We can load them into a magneto-optical trap. We can also then perform subdoppler cooling of these molecules. And we see that the same lambda cooling techniques I talked about earlier actually remain quite effective in these molecules, even though you have many additional states nearby. So we're able to cool the molecules down to about 20 microkelvin or so here in free space. once we've cooled these molecules down, we can then move on to actually loading them into conservative traps. So specifically, we load them into optical dipole traps, and we can load a few hundred molecules within a few hundred milliseconds within this optical dipole trap. So now that we have these ultracold trapped molecules, the first thing we've done is to actually probe what is the actual bending mode lifetime of these molecules. So of course, the bending mode is not an absolute ground state in the molecule, it's a vibration excited state. So this means that this naturally will decay at some rate back down to the ground state or some other state. But we've characterized this quite carefully, and we find that the spontaneous lifetime of this state is on the order of about 600 milliseconds or so. So this seems like it's looks quite promising for future quantum simulation or quantum computation applications, because this lifetime at least should be significantly longer than any sort of gate times you might have. Now, another thing we've lost in moving to this polyatomic molecule is we've lost our ability to do single quantum state control of this molecule. So we need to regain this. So we've been able to do this with a combination of various optical pumping pulses and microwave pulses. We're able to basically transfer most of the population into a single quantum state. And maybe interestingly to point out here is that once we've done this, it turns out there's actually an EDM sensitive state actually right above where we've transferred all our population to, that we can actually now move on to try to do basically a test bed experiment for an electron EDM search in a trapped polyatomic molecule. And so this is a new collaboration that we've had going now for a few months with Caltech out of Nick Hutzler's group. And here the idea is that we basically want to load these CaOH molecules into these EDM sensitive states, which have these co-magnetometer states that help suppress systematics. But one of the actual nice thing here is that it turns out there's also another set of states here that are these 0 G factor EDM states. So these are states that basically have no sensitivity to the external lab magnetic field, but nevertheless they are still sensitive to an electron EDM interaction. And this is of course very interesting for these EDM searches because at many times basically stray magnetic fields tend to be one of the dominant systematics that these experiments have to deal with. So we've been working on actually doing spin precession on this EDM state. So we can basically transfer the population into this EDM state and then perform a spin precession measurement where we apply some sort of external magnetic field such that we see spin precession between this bright and dark state of the EDM sensitive state. And with this, we can then map out, for example, the G factor of this state versus the electric field and find where the zero crossing is, where we have this basically 0 G factor effective state, but still have an EDM sensitive state. So with that, I'd like to conclude the CaOH part, which is we're working now on basically demonstrating the principles of an electron EDM search in these polyatomic molecules. And we're now also beginning to work towards realizing optical tweezer arrays of these polyatomic molecules. But maybe I'd like to conclude with this figure here, which I think summarizes quite nicely the fact that as one adds complexity into your system, it also adds possibilities, whether it be for quantum simulation or for quantum computation or for precision measurements. With that, I'd like to thank the entire CaOH team, so Nathaniel, Christian, Paige, Andrew, and our PI John, as well as our Caltech collaborators, Nick Hutzler and Aryan, as well as our theory collaborators out of Johns Hopkins. And thank you for your attention.